This problem is a reverse of the problems we've just worked previously. In the past, we're given information about motion and we're solving about force. This time, however, we're giving information about force and we're solving for motion. You may notice that there is not any mass given in this problem, and that's because in our equations, the mass is going to cancel out. That means that for any value of mass, 100 kilograms, 10,000 kilograms, the solution for this omega will be the same. If that makes you uncomfortable, you could assume an identity for mass if you would like. So you can assume that it's 10 kilograms or you can assume that it's 1 kilogram. Either way, it doesn't matter because this omega is going to be true no matter what. For this problem, we're looking for an omega that is in a range, so a max and a min that keeps this particle in place. The minimum omega will keep it barely from sliding down. If it were to be any slower, the particle would slide down. The maximum omega is going to be where if it were to go above that at all, that particle would slide up. So drawing the free body diagram, we're looking at it in terms of this mu of n. And because we're looking at the range, we'll put in a value for positive and negative. And that way, when we finish the solution, we'll get two values, one being the top of that range and the other being the bottom. So let's go ahead and get started. Drawing for f of y, with it being 0, so this problem for this equation is going to be a static problem. We get n cosine of theta, that plus and minus mu of s n sine of theta, minus mg equals 0. And there are a lot of unknowns in that equation, so let's go ahead and solve for f of n. And this is not static. It is given an acceleration, and this is given to the book as r omega squared, so we can use that when we plug in values. And we get that n sine of theta plus and minus mu of s n times cosine theta equals mr omega squared. When you're given a lot of tangents and nonsense like that, or sines and cosines, it's easy in a lot of cases to divide one equation by the other. And we'll do that here. We're dividing f of n over f of y. And if you move this mg to the other side, you'll find that the mass cancels as well as the normal force. So we can just write it in much simpler terms, and we leave out variables that we don't have to solve for. And what that looks like is sine of theta plus and minus mu cosine of theta equals r omega squared, and that's without the n and without the m, all over cosine of theta plus and minus mu s sine of theta equals g. Here, the m's canceled out, and here, all of the n's canceled out. So this is a much simpler equation, and here, our only unknown is omega. Solving for omega, you get that g over r times sine theta plus and minus mu of s cosine of theta over cosine of theta plus and minus mu of s sine theta. And like I said before, we have all the values for here, so we can solve directly for omega. And that is 9.81 over 0.2 times 0.5 plus and minus 0.3 times 0.866 over 0.866 plus minus 0.3 times 0.5. And simplifying that down even more, we can get two values for omega. The max is 7.21 radians per second, and the min is 3.41. I don't know why my pen isn't working. Well, 3.41 is the minimum. So if it was to go above 7.21, it would slide up. And if it was to go below 3.41, it would slide down.